All right, so please take a seat. And we can get started with today's class. Welcome to today's class in Mathematics 1. As you remember, we still had a problem that we did not finish discussing on Tuesday. This is this one here. So considering this function, the question was, what is its maximum domain? I've asked you to compute a specific limit, and then the final question, is there a continuous extension of that function to R? And of course, that question alone more or less also encompasses these two here. There's been a tweetback quiz going on, and maybe let's have a look at the answers for the first part. Let's stop that. So you said the maximum domain is the reals without -2 and 1, mostly, and a few other answers. So let's have a quick look at that first. As you can see, this is basically a rational function where both the numerator here and the denominator are polynomials. So the only thing that could go wrong is a root in the denominator. And that means the points where this function may not be defined are exactly the roots of the denominator. So we have to determine the roots of the denominator. So for part A, that's what we do. Determine the roots of the denominator. And in this case, this is x squared plus x minus 2. Polynomial of degree 2. The easiest way to do this is probably using a formula that you all know. The roots of this are given by, let's see, -1 plus minus the square root of 1 squared, that is 1, minus 4 times 1 times -2, that is -8, divided by 2. All right, so we get -1 plus minus the square root of 1 plus 8, that's 9, over 2. So -1 plus minus 3, divided by 2. And that means we get two roots here. The first one is, let's say, -1 plus 3 is +2, divided by 2 is +1. And the second is -1 minus 3, that's -4, divided by 2 is -2. Or, in other words, x squared plus x minus 2 can also be written as a product of the linear factors corresponding to these roots. So the first one would be x minus 1, and the second one would be x plus 2. Right, so that's the factorized version of that polynomial of degree 2. And for the domain of f, of course, that means those roots are exactly the points we need to exclude. So the domain of f is the set of all reals with the exception of -2 and +1. So most of you apparently found the correct answer. All right, any questions about that one? That doesn't seem to be the case, so let's take a quick look at the next part of this problem. So part B asks you to compute a limit of f of x as x goes to 1. And of course that should also be a hint that maybe the point x equals 1 is not that easy to evaluate, so that might be one of those critical points, and indeed it is, right? Turns out that is one of the critical points. Otherwise the limit would be pretty trivial. All right, so before we solve that, again, let's take a look at your answer. So here's what you said. The limit is -2, mostly. All right, what do we do to find that limit? Well, let's maybe just copy that expression here, so I don't have to scroll all the time. So we need to find the limit of f of x as x tends to 1. And that is the limit of this expression. And now if we just substitute 1, we already know what happens in the denominator. 1 is the root of the denominator, so that will become 0. For the numerator, we will get 1 minus 2, that's minus 1, minus 5, that's minus 6, plus 6, that's also 0. Right? So we get something like 0 divided by 0, and of course we can't evaluate that. Okay, so we have to simplify that expression somehow before we can compute the limit. And one way to do that, we already know with factorization of the denominator. We already know that can be written as x minus 1 divided by x plus 2. And we also know that 1 is a root of the numerator. So it should be possible to factor out x minus 1 in the numerator as well. And if we can do this, of course, those two just cancel out, and we get rid of the problematic point. Right, so that would be the idea. So we try to factor out x minus 1. And we do this using long division. Yeah, I need some more space. So this first polynomial, the numerator divided by x minus 1, what will that be? Let's see, let's first look at this highest power here, x to the power of third. We need to multiply x by x squared to get x to the power of 3. And now if we multiply this x squared with this linear factor here, we get x to the power of 3 minus x squared. And then we just subtract that. And that means we got rid of that x to the power of third. And we get minus x squared minus 5x plus 6. All right, so next we need minus x to get that minus x squared here. Oops. If we multiply minus x and this x minus 1 factor, we get minus x squared plus x. And again, we subtract that. So we get rid of that minus x squared. And we get minus 5x minus x, that's minus 6x plus 6. And to produce a minus 6x, we need to have minus 6 here, right? Minus 6 times x is minus 6x. So we get minus 6x and also plus 6. And if we subtract that, we'll finally get 0 here, right? So the division actually works. This here is the remainder. And that means we can express this numerator as x minus 1 and then x squared minus x minus 6. And that is this result here. All right, and now we can just cancel out the x minus 1. So we get x squared minus x minus 6 over x plus 2. And if we now just evaluate that, what we get here is 1 minus 1, that is 0 at -6. So that goes to -6. The denominator goes to 1 plus 2, so that's 3. And that means we can simply substitute x into this expression and we get -6 over 3 or -2. And that is exactly the result that you got as well. All right, so the limit is -2. Any questions about that part? And let's go on with the final part here. So last question, part C, is there a continuous extension of f to the real line? From part A, we already know we need to take care of those 2 points here, -2 and 1. For 1, we know the limit exists. We just computed it, and it's -2. So if we just use that as a function value for our extension, that will be continuous. So we still have to take care of that other point of that -2 and see if it works there as well. So first part of the answer, we may extend f into x equals 1 by setting the function value of the extension to -2, which is computed in part B. And the question that remains is, how about x equals -2? That's the other point we need to take care of. And well, let's do that. Before we do that, let's see what you answered here. And most of you apparently think this will work. Well, what do we have to do? Well, same thing we just did. See if we can compute the limit. So now we need the limit of f of x as x tends to -2. And of course, we can use the simplified version that we had right here. Doesn't make a difference. So let's just copy that over. Ah, damn it. And we need -2 here. Okay, and now if we try to substitute -2, well, what happens? Obviously, this is a root of the denominator, so that would be 0. If we try that here, we get 4 minus -2, that's 6. -6, that's also 0. All right, so we'd get something like 0 over 0. And that means we can try the same thing as we just did, right? Obviously, -2 is also a root of our numerator, so we can again try to factor out x plus 2 here. So that's exactly what we're going to try. X squared minus x minus 6 divided by x plus 2 is, let's see, we need an x first. We get x squared plus 2x. We subtract that and we get minus 3x minus 6. So we need a -3. And we get minus 3x minus 6. And if we subtract that, then we get 0. So as expected, it works out. And that means finally what we have here is x plus 2 times x minus 3. So that's the factorization divided by x plus 2. So we can again reduce that, cancel out the x plus 2 factor, and we get x minus 3. Right? And now we can just substitute the value -2 for x, and we get -5. Okay, so again, the limit exists, and that means we can again extend the function into that point, and then we covered all the gaps. We can extend f into x equals -2 with a function value of -5. And that means the continuous extension, actually exists. All right, so those of you who voted yes had the right solution. All right, any questions about this problem? Okay, if that's not the case, then let's go on with another example problem. Now that one is a nice application, I'd say. Let's take a quick look at that. So what we do in this problem is we consider the temperature along the equator of the Earth. So we have this globe here, and along the globe there is this equator, right? And this is what we're interested in. And what we do is we measure the temperature along this line here, right? So it's a one-dimensional function. We just have this line, and we measure the temperature along the line. And the claim is there is always two antipodal points that have exactly the same temperature. And by antipodal, I mean if I connect those by a line going through the center of the Earth, those two are antipodal points. Right? So points that lie exactly on the other end of the Earth. So the problem is, show there are always two antipodal points along the Earth's equator, or any other line really, with equal temperature. All right, so I'll give you a couple of minutes to see if you can figure out at least the setup and also maybe find the proof. And then we'll discuss maybe first how to approach this problem and then how to solve it. So maybe let's quickly check. Is there someone who thinks they solved the problem already? Someone who thinks they found a good approach at least? Okay, a few. Maybe let's start you off with a few tips on how you could approach that. So we want to talk about the temperature along the equator. I already said basically that is a line, right? It's a circle, so it should make sense to measure the point on the equator as an angle, right? Use a longitude or something like that. So basically we could say, well, this equator here that maps to a line with angles from 0 to 2 pi, right? 2 pi is 1 full rotation, pi is half of a rotation. And we're interested in the temperature along that line, so if we measure the temperature, let's call that T, that will look something like this. And of course, if we rotate around 1 full rotation, then those 2 points here will have the same temperature value, right? So T of 0 and T of 2 pi, obviously that's the same. And of course, that means we can also easily extend that. If we want a function that's defined on R, we can just extend that by making it 2 pi periodic, right? So it's easy to define a function on R that has values in R. Just take that green thing here and append it here and append it here and make that as long as you need, right? So that's the temperature function along the equator. We're interested in seeing whether there is, or whether there are two antipodal points where the temperature is exactly equal. Or in other words, where the difference of temperatures at those points is 0. So to make this a little easier to handle, we define a new function that measures the temperature difference of two antipodal points. And again, we'll define that along the equator to R, and that is meant to measure difference of temperatures at a point X and its antipodal point. Right, so how do we need to define this? Well, let's say we define this as T of X is, well, the temperature at X, that's small t of X, minus the temperature at the antipodal point, and that antipodal point is X plus half a rotation, and that's pi. And of course, as we extended the temperature function to the whole real line, we don't need to take care of any wrapping around or stuff like that. Okay, so what we need to do now is, well, we need to prove that there is a point where this difference is 0. So in other words, show there is some, let's call it X star, in this domain between 0 and 2 pi with T of X star equals 0. And that would mean X star and its antipodal point have exactly the same temperature. All right, so that could be a setup that you can use here. And I'll see if you can prove that. So again, I'll give you a few minutes to see if you can complete that. So let's quickly check how you're doing. Who thinks they've solved the problem now? Who thinks they've at least found a good approach, but are not quite done? Maybe you need a few more tips. All right, two more things I can add. First, let me answer a question that came up actually before you're getting any more confused. Someone said they can't see why t of 0 should be t of 2 pi. So just to clarify what that t is doing, that's measuring the temperature along the equator line. And my parameterization of that line is the angle of rotation around the Earth. Right? So what I do is I start, so this is the center of the Earth, right? This is the point on the surface of the Earth where I start. And this corresponds to an angle of 0. Just any arbitrary starting point, right? And then I start rotating around the Earth. So I follow this circle here. And for example, once I'm here, at that point here, right, that would correspond to an angle of pi over 2. Doing half a rotation, that means here I'm at the antipodal of my starting point, right? That would correspond to an angle of pi. Right, so here's my angle of pi. And then if I go around a full rotation, I'll end up where I started. Right, of course, a full rotation is an angle of 2 pi. And that means after doing a full rotation, I'm at the exact same point where I started. And of course, that means the temperature at that point is exactly the same. Right? Whether I use 0 or 2 pi to describe that point, well, it just depends on which angle I prefer to measure. It's the same point, so the temperature is the same. Right? There is no dynamics, so I don't have to take time into account. I'm just looking at all of this at one given moment in time. And that's why t of 0, this t of 0 is exactly equal to t of 2 pi. Okay, so two observations that are critical to do. The first one is, and that's also the connection to our topic. Someone also asked about where the connection to our topic is. This temperature function is obviously continuous. And that also means this capital T function, the difference of temperatures, is of course also continuous. And then the second tip I like to give is take a look at t of 0 and t at the point pi and find out how those two values are related. There's a pretty simple relation between those two function values. Try to find out which one and you'll be done, pretty much. All right, maybe let's check again. Quick show of hands. Who thinks they found the solution now? Who thinks they at least have a viable approach? All right, so let's see how to do that. Actually, we're almost there. The point is to find that relation, and if you just substitute that 0 here into the definition. Remember, that was how we defined our capital T. You get that what is T of 0 minus T of 0 plus pi, so T of pi. And capital T of pi is T of pi minus T of pi plus pi, that's 2 pi. And this is exactly T of 0, right? 2 pi and 0, same point. So that means what we have here is actually the negative of T of 0. And that's the one point you need to find out. Because now, well, assume T of 0 is positive. What does that mean? That means T of pi is negative, because it's the negative of T of 0. And that means the function is continuous, so there must be a root somewhere in that interval. There must be a root, let's call that x star, of t in that interval between 0 and pi, because t is continuous. And that root is exactly the point we're looking for. And of course, the same argument works if we assume t of 0 is negative. Well, then t of pi is positive. Same argument. Well, and if t of 0 is 0, then t of pi is also 0. And we're already there. Right? And 0 is a root, and we're done. Then we can just use that. Okay, so that's a nice application, I think, of the intermediate value theorem. Somewhat surprising. And someone also asked whether that might be a typical exam problem and whether I should not rather do typical exam problems. And I'd say, of course, in the formulation that I presented here, giving you just that information, that's probably too hard for an exam problem. But I could add something like, look at that function, and then I would first maybe add something like reformulate the question and in terms of capital T, and that is the answer I would expect you to come up with. And then I might add a hint and say, well, show that T of 0 is equal to minus T of pi. That might be a partial problem. And then I'd say, well, use what you have found so far to prove that. And if I give you these sub-steps, these hints along the way, I would expect you to be able to solve that in an exam. It's surely not one of the easiest problems, I'll admit that. But in that form, I'd say that should be doable. All right, questions about that one? Before we go on, maybe. Let's have a quick look at that. I think I covered those, and I covered that. And we'll talk more about the sine function and trigonometric functions probably next week. Those will be nice examples for differentiable functions. Someone also asked whether we'll do any new topics after week 12. So just as a quick outline, next week, week 12, we're going to talk about derivatives and differentiation. In week 13, also in week 12, we'll talk about one important application, and that is optimization, finding local maxima and minima, something you probably heard of already. In week 13, we're going to cover more applications of differentiation. Specifically, we'll discuss L'Hopital's rule. the one that you've been longing for. And we'll also discover Taylor polynomials and Taylor series. Also a pretty important application that you might not have heard of. And then in week 14, we'll cover integration over the real line. And that will be the last new topics that we do. So we'll cover the definition of integration, some integration rules, and of course also the relation between differentiation and integration. And that means we'll have one more week, week 15, where we won't discuss any new topics. That will be the last week of lectures. And that will again be spent on doing Q&As, examples, basically talk about stuff that is relevant for the exam and hopefully helps you master the exam afterwards. All right, that should hopefully answer this question. Good. So maybe let's get to other questions that you've been asking. On the tweetback, I've been asked to talk about problems from the exercise class, specifically 11.3 A and D and 11.4. So I guess that would take about half an hour. And that means if you'd rather try those for yourself first, might be a good idea to get a cup of coffee now and come back for the exercise classes. Otherwise, I'll try and discuss those now and give you a few minutes to think about the solutions, of course. So feel free to go if you'd rather try that for yourself first during exercise classes. All right, we'll start with 11.3a. Okay, we have a limit here there that looks rather intimidating, but actually isn't. So let me write that down first. That's x minus 1 squared, 2x plus x squared plus x times the sine of x divided by x squared 3 minus 2 over x. All right, we want to compute the limit as that tends to 0, and obviously that is problematic because the denominator would be 0 and also this would be 0. So that doesn't look very nice. And of course that part of the expression also would become 0, right? So we have something like 0 over 0 plus this complication here. So again, doesn't look very nice. I'll give you 2 minutes to think about that first. Should actually be rather easy to solve that. All right, I hope that should be sufficient to at least find the right approach. So maybe let's quickly see how to do that. Maybe one word of warning before we do that. You might be tempted, if you know it, to use L'Hopital's here. Please don't. First, because differentiating these beasts here will be awfully complex. You don't want to do that. And second, because it's not even clear whether you can apply that, right? Because, I mean, what is the limit of that expression here? This here tends to 0, but what about this one here, 2 over x? As x tends to 0, this will go to infinity, or maybe minus infinity, or it will jump around widely between those two. So that limit may not even exist, right? If you remember the 1 over x function, of course 2 over x looks pretty similar. That function looks like this. So the limit at 0 doesn't exist, just the one-sided limits would, well, they wouldn't exist either, but they would either be plus infinity or minus infinity. But a limit to 0, you couldn't even say that's plus or minus infinity. That just doesn't exist, right? So it's really hard to say what that limit will be without any reformulation. And if you find the right reformulation, you're done anyway. Okay, what is the right reformulation? Well, if you look at the numerator first, you will hopefully see that there is an x here, here, and here. So you could factor that out first. And that should always be an approach, trying to simplify the expression at hand as much as possible. And if we do that, we're left with this expression. And now obviously, we can cancel this and one of those x's down here. All right, so let me copy that again. And let's cancel that out. Now we're here. And now the next step will be get rid of that ugly expression here. And well, the easiest way to do this is just take that x into the expression. Right? So instead of this, we could also write, well, this is 3x minus 2. Right? That's much easier than this ugly expression here. And now the difficulties have all gone away. That's basically all there is to this. So if you just substitute 0 in place of x, what we get is we get a 1 here. We get 2 plus 0, and the sign of x is also 0. A sign of 0 is 0, sorry. So this will be 2. So that means the numerator goes to 2. The denominator goes to minus 2. So obviously the limit is 2 over minus 2 or minus 1. Right? So this might look terrifying in the beginning, but actually that's just to distract you from the easy solution. All right, questions about that one? And the other one you wanted to see, I think, was part D. So let's also take a look at that. That is the limit here, x to 0 from above, e to the power of x over the logarithm of x. And just so you know, I think we discussed those at the beginning, but basically the behavior of those two functions here, it's always helpful to have that in mind. The exponential function basically behaves like this, right? So it's always positive. As x goes to minus infinity, it goes to 0, and it quickly grows to plus infinity as x goes to infinity. E to the power of 0 would be 1. It's probably the one point you would remember. And well, for the logarithmic function, it's basically reversed. So what we get here is a behavior that looks like this. So that's the ln. That's e to the power of x. Right, so that goes to minus infinity. It has a root, a root at x equals 1, so the ln of 1 is 0. And it also goes to infinity, but pretty slowly. And it's not defined for negative numbers or for 0. All right, so once you know that, it shouldn't be too hard to find out what that limit is. Maybe give it a try for a minute or two, and then we look at the solution. All right, so I think that should be sufficient. Let's quickly see how to solve that problem. Basically, this is all you need, because as x tends to 0, well, what does e to the x do? In that case, we can just substitute the value of 0 for x, right? So that obviously goes to e to the 0, and that is 1. Right, just a constant. Well, what does the ln do? Well, again, just take a look at this one. If x tends to 0, well, the ln goes to minus infinity. So we get something like 1, and the denominator that grows larger and larger and larger. Well, what happens? This goes to 0, of course. And that's it. And if you want to be precise, you could say, well, it goes to minus infinity, and the numerator is positive, so you have something positive over something negative. So this goes to 0 from the left, but that wouldn't be required here. Question? Sorry? So why is that infinity not a problem? Okay, so usually I say if we divide something by infinity, that can be everything. In this case, this is not a problem because there is nothing that's working against it, right? So this here goes to a simple constant that is not zero. So there's nothing to cancel out that infinity effect in a way. You only have problems if you have two effects that go into different ways. So if you have something like infinity over infinity, or infinity plus or minus infinity, or 0 over infinity, or infinity over 0, things like that. Yeah? In that case, those two, well, 0 over infinity is not a problem actually. 0 over 0 is a problem. Things like that, yeah? So if you have two partial limits working against each other, then you can't really say what happens. In this case, that's not the case, yeah? This first limit, this numerator, that just tends to a constant, so no problems there. Okay? Any other questions? Otherwise, let's take a look at 11.4. You also wanted to see that, or some of you wanted to see that. Actually, that's an exam problem from quite a few years ago, 2015, 16 or something like that, I think. I've seen that on some exam. So E11.4. So here's this function, 24 minus e to the power of minus 1 over the absolute value of x divided by 2. Divided by 2 is not really important. And the question is, determine the maximum domain of f, determine a continuous extension of f to R, and then determine the image of f. So the last question is kind of a bonus. But A and B, that should be something you're familiar with. Let's give that a try. All right, maybe let's talk about A and B first. So A, maximum domain, that should be pretty obvious. The only complicating thing in here is that 1 over x expression. Right? The E function is defined on the real line. There is no x here in the denominator, so the only problem appears here. And here, of course, the denominator may not be 0. So what we need to exclude is the case that x could become 0. And that means our domain is the reals with the exclusion of 0. Well, that's the solution of that first part here. For the limit, where we need a continuous extension of f to r, knowing that the only problem is that 0 point here, because otherwise, well, the E function is continuous. And, well, this is, again, just a combination of continuous functions here. So nothing unexpected could happen with the exception of that 0 point here. The thing is continuous everywhere. We just need to compute the limit at 0. Right? So B is just saying compute the limit for this critical point. All right, so that's what we need to do. We need to compute the limit as x goes to 0 of f of x, 24 minus e to the power of minus 1 over the absolute value of x over 2. Now, if you have absolute values in there and want to get rid of those, one possible way would be to do one-sided limits, and then you know the sign of x, and that means you can get rid of that absolute value. In this case, you don't have to do that. It's easy to see what happens even without that. But still, let me show you just for illustration how you could do that, right? So we could resort to first computing the one-sided limit as x approaches 0 from above. That means x is always positive. Right? We can assume that. And then we just get e to the power of minus 1 over x, right? In that case, the absolute value of x is just x. Okay, and now what happens here? Well, as x goes to 0, this part of the expression that goes to infinity. That means, use another color, this part of the expression, including the minus, goes to minus infinity. And well, what happens with the e function if the argument goes to minus infinity? Well, the function goes to 0. Right? I find it always helpful to have these little sketches here in mind. So if I'm dealing with functions like the ln, the function, sine or cosine or things like that, I always make a little sketch just to remind me how that function looks like and how it behaves. Okay, so that means this whole thing here, that tends to 0. And that means the limit is simply 24 minus 0 over 2, and that's 12. All right, and just for the sake of completion, let's also look at the one-sided limit from below. So in this case, we know that x is negative, and that means the absolute value of x is the negative of x, right? The absolute value of a negative number is its negative. So the absolute value of minus 5 is minus 5 or plus 5. And then if you want to get rid of that absolute value, we could just use that fact and say, well, that's e to the power of minus 1 over minus x over 2, or 24 minus e to the power of 1 over x over 2. And now again, this 1 over x, if x goes to 0 from below, so the x's are negative, that means this will go to minus infinity. And again, that means e to something that goes to minus infinity, that will go to 0. Right, so again, we get 24 minus 0 over 2, or 12, same value. And of course, we could have skipped that division into two parts. simply because we could have argued, well, no matter what sign x has, this here is always non-negative, positive, right? So this is the only argument we'll ever need, basically. But just in case you'd rather work around that absolute value, because in some cases it might be helpful to get rid of that first and then make the argument, I wanted to show you how to do that. All right, so that limit is 12, and that means our continuous extension well, let's call that f bar, is defined on R by saying, well, it's f if x is not 12, sorry, not 0, of course, not 0, and it's 12 if x is 0. So we just extend it by filling in that gap. All right, questions so far? Yes. If x tends to minus infinity, then what? 1 over x tends to 0. That's right, yes. If x... Sorry? E to the power of 0 is 1, correct. Could we get to that? Because what we're computing here is the limit as x tends to 0, not to infinity. We'll get to that in a minute. You're thinking about C already. So let's talk about C, yeah? if you're there anyway. Part C, determine the image of f. Well, in this case, we have to make an argument that's just a little more involved. We do know one function value so far. We do know that value of 12 at the point 0, right? So f at 0 is 12. Let me again write down the term for f so I can point to that. 24 minus e to the power of minus 1 over x absolute value over 2. So the only x that appears in this term is here, and that only appears as the absolute value. So it doesn't matter what sign x has, whether it's positive or negative, the function value will be the same. Or in other words, the graph of that function will be symmetric with respect to the x-axis, right? So let's write that down. So this is symmetric with respect to the y-axis. So what I have so far is I know the value of 12 here. And I know the behavior of the function is going to be symmetric. And now let's think about what happens if we increase the value of x here from 0. Well, if we have a value that grows, then of course that means this here will decrease, right? What happens with this one here? E to the power of minus something. Well, if that decreases, of course this here will also, this will increase, sorry. And now what we have is something minus this increasing argument. So the value of that will decrease, right? 24 minus something increasing will decrease. That means when x grows, the function value will decrease. So x increases, f of x decreases for, I just made that argument for positive x, yeah? Of course, for negative x, it's just the reverse by symmetry, right? If that increases, basically it works towards the y-axis, and that means the function value will increase towards 12. So we have a behavior that pretty much looks like, well, Here we have 12, and from that point on it decreases. The only question is, will it ever stop? And if so, where? So what we need to figure out is, what is the limit of f of x as x increases to infinity? And that's what you wanted to do, right? So I'll give the rest of you a couple of minutes to figure out that limit. All right, so let's complete that. We need to figure out the limit as x tends to infinity of f of x. Let's write down the function definition once again. It's 24 minus e to the power of minus 1 over absolute value of x over 2. Now, of course, x going to infinity means we can safely assume x is positive. right? So we could just do without the absolute value if you want to. And that means if x increases, then of course this expression here will go to, if x increases, will go to 0. E to the minus 0, well, that is a simple function value. We can just substitute that. So that means this will go to e to the 0 or 1. And that's all there is to this limit. So in other words, what we get is 24 minus 1 over 2, or 23 over 2. Right? So what happens is the function looks like this. We have a value of 12 here. And from that point on, it decreases very slowly till it hits a value of 23 over 2 here. And it's symmetric, so the same behavior is on the left, and I wrote that in a very bad way, so 23 over 2. So we can just map that over here. And that means the image of the function, the image is just the set of all function values that are assumed. The image of that function is therefore, well, what function values do we get? Well, we get anything that's between 23 over 2 and 12. Twelve is obviously included, that is assumed at 0. 23 over 2 is not included. That function value will never be assumed, so that would be the correct image. All right. Any questions about this problem here? Yes. Okay, so if you want to compute the image, yeah, you're right. The statement is not that precise. I should have asked for the image of the continuous extension of f. That would be more precise. Yeah, that's correct. Otherwise, you could always argue, well, 0 is not included in the domain, and in that case, you would have to exclude 12. That is right. Actually, it was exactly the formulation in the exam. I wonder how that was graded. But it wasn't my exam, so I wouldn't know. Any other questions? All right. So I'd say that's a good point to call it a day, or at least a lesson. Of course, you're welcome to stay for exercise classes, though. And otherwise, I'll see you next week when we start our discussions of derivatives and differentiation.